Everything from our phones to our cars, our entire modern world, it all runs on batteries. And because of that, there is this massive global race to build a better one, a breakthrough that could really unlock a sustainable future. Well, this new research, it might have just found the secret recipe. So here's the fundamental problem we're all up against. We need our energy storage to be cheap, right? And we need it to be made from stuff that's easy to find everywhere on Earth. And of course, it has to pack a huge punch. The trouble is, with today's technology, you can have any two of those, but you can't have all three. So on one side, you've got the reigning champ, lithium-ion batteries. They are super powerful, no doubt. But lithium is pretty rare, it's expensive, and the whole supply chain is, well, it's fragile. But then you have sodium-ion batteries. Sodium is literally everywhere. Think table salt. It's dirt cheap and abundant. The catch has always been that big challenge. They just can't hold nearly as much energy. At least, that was the story until now. So how in the world do you solve that capacity problem? Well, the answer turns out to be a really clever and frankly powerful bit of chemistry. It's all about getting a part of the battery that we usually ignore to step up and do some of the really heavy lifting. Okay, so in a normal battery, the energy is stored and released by metal ions, which are called cations. In this case, we're talking about ruthenium. This whole process is called Catonic Redox. Think of it like a standard car engine. It's reliable, it gets the job done, and it has powered all our gadgets for decades. But, a standard engine has its limits. To get way more power, scientists have been trying to fire up something called anionic redox. This is where you convince the non-metal atoms, the anions, which here are the oxygen atoms, to get in on the action and start storing energy too. So if cationic redox is the engine, activating anionic redox is like strapping a massive turbocharger to it. In this image right here just shows it perfectly. Those blue steps, that's the energy you get from just the metal, the ruthenium. But by waking up the oxygen, that's the red steps, you add this whole new tier, a whole new level of energy storage. You can literally see the potential capacity to shoot through the roof. But there's a really good reason this turbocharger isn't in every battery you own. For years, trying to unleash this kind of power came with a really serious and often catastrophic downside. Here's the problem. When you get that oxygen too excited, the whole internal structure of the battery just starts to fall apart. And even worse, those oxygen atoms can actually just escape as a gas. And that's not just bad for capacity, it's permanent. The battery basically just self-destructs. It degrades incredibly fast. So this right here became the central challenge. Everybody knew this incredible power was just sitting there, locked away inside the oxygen. The billion-dollar question was, how do you get that power out without completely destroying the battery? How do you get the turbocharger without blowing up the engine? And the answer this research found comes from some truly beautiful engineering, right down at the atomic level. Instead of just using the material they had, they decided they were going to rebuild it, literally atom by atom, to give it the exact properties they were looking for. The strategy is called alliovalent doping. Now, I know it sounds super complex, but the idea behind it is actually pretty simple. You take the battery's main material, and you just strategically sprinkle in a few different atoms. You swap some of the original guys out for new ones, and that one little change completely rewrites how the material behaves. So how they actually do it? Well, they started with their base material, and then, like master chefs trying to perfect a recipe, they systematically replaced a tiny bit of the ruthenium with other elements, things like tin, magnesium, and aluminum. The whole goal was to see how each tiny little substitution changed the entire structure. Every single swap created a brand new custom-designed material. And right here, you can see exactly what that looks like down at the atomic level. On the left, that's the original pristine crystal. But on the right, that's the new structure after they've doped it. See how a few of those purple ruthenium atoms have been swapped out for the blue aluminum atoms? Now, that might not look like a huge change, but by tweaking that atomic framework, you totally change its electronic properties. And that has huge effects on how the battery performs. So, after trying out all these different atomic recipes, one particular element turned out to be the hero of the whole story. It created the absolute perfect balance of power and stability that they had been searching for. All right, let's dive into the data and see what's really going on inside this thing. This first chart is our starting point, the original, undoped material. Now just focus on those two lines. The blue dashed line, that's the ruthenium, our standard engine. You can see it's active, it's working. But now, look at that red line for oxygen. It's almost completely flat. That tells us the oxygen is doing absolutely nothing. The turbocharger is completely off. Okay, now watch what happens when they add aluminum. This is the exact same test, but on the new doped material. The ruthenium engine is still doing its thing, but just look at that red line. The oxygen contribution has absolutely skyrocketed. It's now awake, it's active, it's storing and releasing energy. They didn't just switch the turbocharger on, they got it working in perfect sync with the engine. This one graph, this is the money shot. It tells the whole story. Over on the far left, you have our original material, where ruthenium, in blue, does everything. But as they start introducing the different dopants, as you move from left to right, you see this beautiful systematic handoff. The work done by ruthenium goes down steadily, while the work done by oxygen in red takes over more and more. This is the proof. This shows they figured out how to precisely control and tune that turbocharger. And in the end, the clear winner was aluminum. It didn't push the oxygen so hard that it broke the battery, which is what some of the other dopants did. No, it created this perfect, just right zone. It activated that massive capacity boost from the oxygen, while at the same time maintaining the structural stability you absolutely have to have for a safe, long-lasting battery. Okay, so this is so much more than just a cool science experiment. The principles they uncovered here could have massive implications for the future of how we store energy. So what are the big lessons here? Well, the researchers basically wrote a new rulebook for battery design. They proved that the chemical bond between the metal and the oxygen, that's the critical knob you need to turn to tune the turbocharger. And most importantly, they figured out that using a dopant like aluminum is the secret to getting both parts, the engine and the turbo, to work together safely, preventing the whole thing from self-destructing. And honestly, this is the most important part of all. They didn't just stumble upon one lucky recipe for one good battery. What they've really done is create a roadmap, a whole design philosophy that other scientists can now take and run with to engineer a whole new generation of powerful, cheap, and abundant batteries for absolutely everything. Which leaves us with one final and pretty exciting question. After all these years of being the weaker, less powerful sibling to lithium-ion, could this be the breakthrough that finally lets sodium batteries take center stage and power our world with an element that's as common and cheap as salt?